So multiple bonds. What about those p orbitals? So this is where the double bonds come from. If you have, sigma bonds are caused from head-on overlap between either s orbitals or between s and p orbitals or between s and, in this case, an sp, like an sp and an sp orbital. So that head-on overlap causes a sigma bond. But what you can have is in the the p orbitals that are not involved in the overlap. For example, if you got sp3 and you have an sp2 and an sp2 that are bonded together, you have these unoccupied pi bonds, and you could put electrons in those orbitals as well. You have essentially sideways overlap to form a pi bond. So a double bond consists of a sigma bond and one pi bond, and a triple bond consists of a sigma bond and two pi bonds. And this explains to some extent why a double bond is not quite twice as strong as a single bond, as we saw, looking at bond strengths, because the pi bonds don't overlap as well because they've got the sideways overlap instead of a head-on overlap. They have less overlap and therefore contribute less to the strength. So a double bond is less than twice as strong as two single bonds, because two single bonds are two sigma bonds. A double bond is a sigma bond and one pi bond. So examples, ethylene, C2H4, if you look right at the Lewis structure, you get a carbon double bonded to a carbon and then single bonds to hydrogens. So the carbon atoms are sp2 hybridized, and you have trigonal planar geometry around each carbon. If you look at the molecular orbitals, and this is the molecular orbitals caused by overlaps of the atomic orbitals, the sp2 orbital and the extra pi orbitals, that this is the sort of picture, qualitative picture that you get, is that the bond consists of the sp2 orbitals of the carbons that are not interacting with the hydrogens interacting head-on, and the p orbitals that are not participating in the sp2 hybridization, creating another orbital, and those show those have two electrons as well. If we do if we look at the Lewis structure here, then there's C2H4 will have a total of 4 plus 4 plus 4 electrons. So four valence electrons. So let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are all the 12 valence electrons. And as we can see from the Lewis structure, they're all occupied in some sort of a bond. Either a sigma bond here between the S and the sp2, a sigma bond, sigma bonds, we already counted for those, sigma bonds there between, created by the overlap of the sp2 orbitals of the carbons, or in the pp overlap to create a pi bond of the two carbons. So that is an example of the molecular orbitals creating sigma, the molecular orbitals resulting in sigma and pi bonds that result from the combinations of the atomic orbitals. Okay, let's dig a little deeper than this. Triple bond. So ethine or acetylene is C2H2. Doing the Lewis structure, you get a triple bond in the middle in order for the carbons to have a complete octet. And so what you get one sigma bond formed by sp-sp overlap, right there. There, the orbitals in carbon, you have one s and one p combining, and then that leaves two p orbitals left over like this. And so there's two pi bonds and one sigma bond. Let's do some electron counting again. So right here, we've got 4 plus 4, 4 valence electrons from carbon, 4 from carbon, and then 2 more for hydrogen, so 10 electrons. So there's, the sigma bond has, this sigma bond has 2, this sigma bond has 2, this sigma bond has 2, and then each of the pi bonds, there's 2 in this pi bond and 2 in this pi bond, for a total of 10 electrons. So all these, each of these colored orbitals, here's 2 electrons, here's 2, here's 2, here's 2, and here's 2. All of these orbitals are colored in because they occupied by pairs of electrons. So all the valence electrons involved in bonding here, some in sigma bonds, some in pi bonds, because the different electrons are combining to form different atomic orbitals where the electrons are stored combine to form orbitals, molecular orbitals, where the electrons are stored after bonding. Acetic acid is shown below. The geometry about C1 is tetrahedral. C2 is trigonal planar, and O1 is bent. What is the hybridization of the orbitals around C1, C2, and O1 respectively? Okay, so if this is trigonal planar, then almost certainly it's going to be, well, it has to have sp3 hybridization. Otherwise, if it wasn't tetrahedral, it wouldn't have sp3 hybridization. Remember, if you go down to like, you know, hydrogen sulfide, then you can get something that's not sp3 hybridization. But for carbon, it's going to be, if it's bonded to four things, it's going to be tetrahedral. Okay, and so that we got, you know, approximately 109.5 degrees in all these angles. So C2 is trigonal planar. So it's trigonal planar, you notice that there's a double bond here. So this is absolutely going to be sp2, and you're going to have about 120 degrees. And then finally, for the oxygens we know the Lewis structure involves four separate electron densities. And so we know there's actually also lone pairs here and here. This is also sp3 with this angle, you know, a little less than 109 degrees because the lone pairs take up too much space. So we have two sp3s and one sp2. And you know, this becomes actually quite important because the shape of organic molecules like this, exactly what the angles are and what the geometries are quite important for molecular recognition. If you're looking at, you know, protein drug binding, some of the research I do involves that, knowing what the geometries are pretty important. And we actually, in a collaboration that has a big grant, the Open Force Field Initiative, where we're actually going through and determining, for the molecular models that we, you know, simulate protein drug binding with, we go and we're actually having to go through and like use quantum mechanics to calculate these angles and bond lengths more precisely in order to describe exactly what's going on in these molecular in the atomic geometries, because you need to get the atomic geometries right to do these complex problems of molecular recognition. Okay. So one more example, this is my favorite one here, Olene, C3H4. So what does it look like? You've got an sp2 hybridized carbon here, an sp2 hybridized carbonized here, and an sp hybridized carbon here. And so we know, looking at it, that we're going to have you know, we have double bonds. So the carbon in the middle has two pi bonds, but and that's not like a triple bond. It's two pi bonds in two different directions. So the crazy thing is, and this is showing how this theory actually works, that if you actually look at it in 3 dimensions, you have trigonal planar geometries for both of the carbons on the end, but they have to be perpendicular trigonal geometries to each other. Why? Because one of the, you know, the one in the middle, it has two pi bonds. You know, it's got an sp3 hybridized, sp hybridized orbitals that are bonding with the two other carbons. So this is sp here. This is sp here, and so there's two pi p orbitals available for pi bonding, but they're perpendicular to each other. There's the px here and the py here, and so when it forms those pi bonds with the lone, you know, this is sp3, sp2 here, sp2. So you have an sp2 sp bond. Then this one is only free to interact with you know, px, and this one is only free to interact with py. So because of how because you know, you've only got two p orbitals and there's perpendicular to each other, the pi bonds have to be perpendicular to each other, and therefore the hydrogens are perpendicular to each other as well. So examples like that, and you can, you know, do calculations or experiments and see that indeed the molecular shape is that the two trigonal planar carbons have their hydrogens perpendicular to the others. So that's, I think, a really cool example of how this geometry all works together. So that's about as far as we can push molecular geometry with valence bond theory. We'll talk next time about molecular orbitals.